Now we are going to see a new concept which is called unification, and something to do with terms and making them equal with each other. Let's see what it entails. So first, try to see there is a game of terms. Means when you're trying to do reason over first order logic, you need to make several terms equal and based on do the reasoning. Let me motivate what is going on here. This is the proof we did in some couple of lectures earlier, and we showed this formula was valid. Now let us try to prove it via FOLCNF. How do we do that? We negate this formula and turn into FOLCNF. We obtain this formula, and these are the clauses which we get after doing classification. And in this case, I am not dropping my first quantifiers, and you see that there is one constant symbol has showed up because of this columnization. Now I'm going to show that these three formulas together going to trigger contradiction, and therefore this guy is valid. So let's continue. Okay, so we have these three formulas. First, I will use assumption to introduce not QC in our proof steps. And then I will pick the formula, this one, and get for all x, px or qx. Naturally, I can eliminate for all x, and I simply just keep the same variable. I say px or qx. Move on, and we're now going to introduce the third formula in, and again, I can use for all lim and get not of pfx. Okay, I got these two formulas. I can do resolution between them because I have a not of p of x and p of x there, and this we apply resolution and we obtain q of x. You see this q of x and not of q of x look very similar, but they don't have same name here. There's x is sitting there, c is sitting there. So I need to somehow from x to turn into c. How do I do that? Okay, so first I need to bring back the quantifier for all intro because x is not being referred here, so I can just say for all x qx, and then apply the for all lim, and instead of introducing x, now I am allowed to introduce any term, so I can just introduce c here. Now using this fact and this fact, I can introduce a contradictory statement where a formula and its negation both are conjunctive. Therefore I have derived contradiction, and therefore sigma is unsatisfiable, therefore my original formula is valid formula. One important step to notice here is this step. Here from x I found c. How did I decide to choose c to do this instantiation? That is the one of the key difficulty of doing first order logic proving automatically. You need to find these terms, and finding these terms may be very simple here. You can see that there's x and there's only c. You can do there, you can just put it right. But now I'm going to show you that this is not always so easy. You need to have some something more going on, just simply observing that you need c and just use c. So now let us look at an extreme example for finding the magic term. For example, we found c there to instantiate some universal quantifier. This time we will see that it's not so trivial to say. So let's take this formula, and we will show that from this formula I can derive contradiction, and therefore its negation is a valid formula. Probably that's how it gets used. Okay, so let's see how do we do that. This formula derives itself, so it will say that you have this as a assumption. Now what you do, for all lim I do, and I remove x4 and then don't change the variable name and just keep it as x4, no problem. Now I will move on and try to eliminate x3. For x3 I want to pick a term in such a way that it makes things more and more equal. So I want to make this x3 equals to j of x4. So I can just simply put x3 to be j of x4. So I will do that. Now I want to eliminate x2, right? And x2 in a way such that things get more and more equal. Okay? So if I do that, you see the x2 also occurring here. So if I put it here something, and then also this guy will get changed. Be mindful that if you make some changes, it has a long-ranging impact. What should I choose? Let me choose x2 equals to this term. Okay, it makes this term and this term equal. Now what we are left with, x1 is still universally quantified. Now I have to get rid of x1 also, and such that both sides become equal. So now this guy can be replaced by another term, and then now you can see that these terms are chosen in a way that the left hand side and the right hand side look exactly the same. Now let us see that the first point is here. Now these terms are equal, therefore I have derived contradiction. It's not exactly the contradiction. You have to do a couple of more steps to say contradiction, because first you introduce like this term equals to this term using reflex rule, and then put them together, then you say now it's a contradiction. Okay, there are two extra steps involved. Anyhow, so the question remains, how did we find these terms? So we need a mechanism to auto-detect substitution such that the terms with variables can become equal, and then you say, okay, you're saying these two disequal, but look, they're exactly the same. How can that be the case? Or you can do resolution because you need literals exactly matching to apply resolution. Then also you need that. So in various contexts it may be useful. So making terms equal seems to be very desirable. In the previous example, we asked to equate these terms, this term, first term and the second term, okay, this one and this one, by mapping x1, x2, x3, x4 to some other term such that they become equal. Right? This process is called unification, and sometimes the unification may not even be possible. If I give you two terms and I say, okay, unify them, it may not even work. Okay, it's not possible to unify. So we will study when terms are possible to unify, and if they are possible to unify, how can I find that unification mapping.